Okay, so today we're going to work a couple of problems from chapter 15. Um, the first ones we're going to do have to do with heating curves, and they're going to harken back to some things we learned in chapter 14. So this is going to be a little bit of a review. But if you'll recall, a heating curve looks something like this. Worked with these in lab this week. But you have time on the x-axis here, and temperature generally on the y-axis, and usually you have something that goes up and then goes through kind of flat places and then goes up and then again goes through kind of flat places and then goes up. And these regions that are flat correspond to phase changes. So we have phase changes here. And so, for instance, in this first problem, well, the basic idea here is that during this course of time, however long this time is, let's say that this is over the course of 1 hour or something like that. Over this course of time, we have a constant heat being added to our substance. So we're constantly adding, in the problem example 15.1, we're adding 250 joules of heat every minute. So constantly adding 250 joules every minute. And so here we've got 60 minutes tapped off. And so during the first part, the heat actually increases the temperature of our substance. During the second part, the heat is used to change the substance from one phase, presumably the solid phase, into another, presumably the liquid. And then the temperature starts to go up again, and then we have another phase change area here. And this is presumably, so this one is probably going from solid to liquid, and this one is probably going from liquid to gas, and then the temperature continues to rise. And so we've kind of, in class, we kind of just went through this in kind of a way of just kind of descriptively describing what's going on here. And with these problems, we're going to more quantitatively work out exactly how much energy or how much time is associated with each one of these things. So you'll notice that in these regions where the curves are, where the temperature is rising, for instance, this region right here, we've learned how to do this before. We know that the heat absorbed is going to be equal to the mass times the specific heat capacity times the change in temperature. So this change in temperature, notice that this is a change in temperature, is going to be related to the heat absorbed, the mass, and the specific heat. Or, one we use less, but we will use in this problem, we could have the number of moles and the molar heat capacity times the change in temperature. These are really two different ways of looking at the same thing. This top equation is in terms of the mass, the mass of the particles present, and this is in terms of the actual numbers of particle present. So specific heat capacity and molar heat capacity are two different things. Remember, the units on specific heat capacity are joules per gram per degree Celsius. Per degree Celsius. And these need to have minus ones. And this is going to be joules per mole per degree Celsius. And remember, when it comes to changes in temperature, then we are okay to use either kelvins or degrees Celsius interchangeably. It's fine to use either one that we want for a change in temperature, because the change in temperature in the Kelvin scale and in the Celsius scale are identical. If you go up 10 degrees Celsius, that's the same thing as increasing 10 Kelvin. Okay, so that's the basic picture of what we're going to do here. Now, what we need to figure out is what to do about these portions, and we've talked about it before. But in these sections here, we're dealing with enthalpies, changes in enthalpy, and typically it depends on what we have here. So here we have a liquid going through the gas phase. That's called a vaporization enthalpy. And then here we have the solid going to the liquid, and that's called fusion. So remember this delta H enthalpy. This is just Q at constant pressure. So this is the amount of heat absorbed, or released at constant pressure. So most of our experiments we do at constant pressure. We just do it whatever pressure the room pressure happens to be. And so usually the heat exchange during an experiment in a typical laboratory experiment is equal to this quantity H, which was the enthalpy. Okay, so this is what the definition of enthalpy is. And so we're going to use that in this picture to solve this problem. So let me just go ahead and erase some space here. And we'll kind of redraw this picture as we need it for the problem at hand. Okay, so what does the problem ask? It says, how long will it take to heat 50 grams of ice, H2O solid, 50 grams of ice from at 0 degrees Celsius, to liquid water at 100 degrees Celsius. So, excuse me, our picture is we have our heating curve. We have starting at 0 and we're going up to 100. And this is our temperature in units of degrees Celsius. And our heating curve is going to look something like this. Because we start with ice, it's going to be flat as the ice melts. And then it's going to go up to 100 degrees. Now if we keep heating it, it's going to flatten out here as well. But this is where we actually want to stop. We want to know, what is this length of time? How much time is elapsed to go through this portion of the curve? How much of that time was there to go through this portion of the curve? So to calculate that, we have to calculate two things. We have to calculate how much heat was required to melt the ice. That's the melting portion here. And then there is a region here where we have to heat up the water. So this is warming the water. Each of these things requires heat, and we need to see how much heat they require and then find out how long that will actually take. Okay, so that's the basic structure and setup of the problem. We are told that the heating rate is 250 joules per minute. That means that every minute that ticks off on this axis, this x-axis, is an additional 250 joules of heat added to our system. And we're told that the molar heat capacity is 75.3 joules per mole per Kelvin of liquid water. Okay, so this is the molar heat capacity of liquid water. Okay, so we have two things to calculate. The first thing we need to calculate is the energy required to melt the ice. The energy required to melt the ice. Okay, so the heat required to melt the ice is going to be Q, that's the heat required to melt the ice, is going to be equal to the number of moles of ice, so how much ice there is, times the enthalpy per mole, the enthalpy of fusion per mole. So what this says is the enthalpy of fusion, that tells you how much heat you need for 1 mole, and then we multiply that by the number of moles. So the first thing we need to do is figure out the number of moles of ice, and let's just remember how to do that. If we start with 50 grams of water, 50.0 grams of water, and we're going to do this thing where we multiply to make sure our units cancel appropriately. What do we know if we go to the periodic table? That there are 18.02 grams of water for every 1 mole of water. And if we plug that into our calculator, we'll get 2.77 moles. So we have 2.77 moles of water in this problem. And that's what goes here. Okay. Furthermore, if you go to a table, and you'll have to do this for these problems, this would of course be given to you on a quiz or a test, but on your homework, you'll have to look this up. You can actually look up this value. It's in the textbook. You can look it up on Wikipedia. There's lots of different places to look it up. But at 0 degrees Celsius, the enthalpy of fusion is 6.01 kilojoules per mole. So if we plug everything in here, how many moles of ice do we have? We have 2.77 moles. And we're going to multiply that by the enthalpy of fusion. Again, you look this up on the internet or in your textbook, and you will find that that is 6.01 kilojoules per mole. Okay, units of moles cancel out, and so we have a unit of Q, which is heat, and so that's 2.77 times 6.01. That's 16.6 kilojoules. Now, this is the amount of heat that is required to do this portion of the curve. That's how much heat we need to get through this flat portion of the curve. Okay, so that's the heat for melting the ice. Now we have to calculate the heat for warming the ice. So actually it's not warming the ice anymore, it's the warming the water from 0 degrees Celsius to 100 degrees Celsius. Okay, so how do we calculate this? Well, we calculate this the same exact way that we calculated this last semester, which is that we have Q, the heat associated with this process, is equal to the number of moles times the molar heat capacity. Now, we could go look up the specific heat capacity and use 50 grams times specific heat, but that will be the exact same number as moles times molar heat capacity. So these are really just two different ways of doing the same thing. It's actually the exact same number once you do the calculation. And then we have to calculate what delta T is. Delta T is always T final minus T initial. Remember, this is the definition of delta T. Okay, so we can just start plugging things in. So we have Q is equal to N, that's 2.77 moles, times molar heat capacity is given in the problem, that's 75.3 joules per mole per Kelvin, times change in temperature, that's 100 minus 0, and it doesn't matter if we use Kelvin or Celsius. So that's 100 minus 0 is 100 Kelvin. Okay? So you plug all of this into your calculator, and what you'll get is 2.086 times 10 to the 4th joules. Okay? All right, so we have two processes. This first process of melting the ice requires 16.6 kilojoules of energy, or 16,600 joules of energy. And this second process of warming the water from 0 degrees up to 100 degrees requires 2.086 times 10 to the 4th joules of energy. So the last thing is we want to know what the time is. How long does this take? And we're given our rate of heating. So 250 joules every minute. And so what we're going to do is we're going to calculate how long it takes to melt. So how long it takes to melt, the time is going to be the fact that we used 16.6 or 16,600 joules of heat required, and we see that for every 1 minute we supply 250 joules of energy. So notice our joules cancels out. So every 1 minute we supply 250 joules of energy. Punch that into your calculator and what you'll get is 66.4 minutes. So this takes 66.4 minutes. And then we do the same thing for warming. And so what do we have here? We have 2.086 times 10 to the 4th joules, and we're going to multiply that by the same thing, 1 minute for every 250 joules. And when we punch that into our calculator, we get 83.4 minutes. Okay, So this is the amount of time it takes to melt the ice. This is the amount of time it takes to heat the ice up at this particular rate of heating. Now, of course, we can heat it much faster. We can put it on a higher heat source. This thing depends on how fast you're heating things, but at this rate of heating, this is how long it will take to do this process for 50 grams of frozen ice at 0 degrees Celsius. Okay, so we add these two things together, so our total time is going to be 66.4 minutes plus 83.4 minutes, and that will be equal to 149.8 minutes. So this time here, from 0 up to the point where the water reaches the boiling point but doesn't actually start boiling away, is 149.8 minutes. Okay, so there's a lot of stuff here. This is a good review from chapter 14 if you don't remember how to do all these things, but they're basically two different equations that you have to pay attention to. The first one has to do with whenever you're going through one of these phase changes. The phase change depends on the number of moles of substance times the enthalpy associated for the standard enthalpy associated for that phase change. The temperature change does not involve a phase change, and we're going to generally calculate that one of two ways. We either calculate it with Q is equal to mass times specific heat capacity times our change in temperature, or this is also going to be equal to number of moles times molar heat capacity times the change in temperature. So hopefully this helps with some of your homework problems.